Now we're going to introduce the quantity called the dot product. The dot product is one way of multiplying two vector quantities together. So if I have vector A and vector B, I can calculate the dot product between these two things via this definition. We're going to essentially represent the dot product with A and a heavy dot in between these two vectors as far as the notation is concerned. And when I'm dot producting two vectors, I'm going to be multiplying their horizontal or their x components together, a1 times b1, and then we're going to add that to the y components multiplied together, a2 times b2, and then we're going to add that to the z components multiplied together, a3 times b3. And then when we calculate all of that, we call that the dot product between these two vectors. Now, the dot product, when I'm multiplying or dotting two vectors together, notice that A, of course, is a vector quantity, and B is a vector quantity. But when I calculate the dot product, A dot B, that result is going to be a scalar quantity. And again, a scalar quantity is basically any real number. A scalar is just the counterpart of a vector. Vectors are vectors, and anything that's not a vector is a scalar. It's basically just a number. So in this first example, we have two vectors, and we're going to calculate the dot product. Now, normally we'll see this as a heavy dot in between those two vectors, indicating that I'm looking at the dot product. The dot product is defined to be the scalar quantity that results from taking the x components and multiplying those together. So we'll say 4 times 0. Now this is a scalar product right here because these two are numbers, so we're basically just, that's kind of not quite the heavy dot, but it's the traditional soft dot that you see when I'm multiplying just two real numbers together. And then we'll add that to the y components that are multiplied together, and so we'll say -1 soft dot to the multiplied by the 2, and then we're going to add that to the z components multiplied together, and so that's going to be 2 times 5, and then we figure out what this quantity is. So A heavy dot B, the dot product between two vectors, is going to be 0 minus 2 plus 10. So when we combine all those quantities, we see we actually get the scalar quantity, which is +8. +8 is not a vector, so it doesn't have a vector hat, and that is the dot product of those two vectors. If I were to take vector A and dot it with itself, essentially that is taking the vector A and we will multiply it by its own x, y, and z components. So A dot A is going to be 4 times 4 plus -1 times -1 plus 2 times 2, and the dot product of vector A with itself is going to be 16 plus 1 plus 4, which is 21. Again, when we dot product two vectors together, we get a scalar quantity. 21 is not a vector, it's just a real number, so we call that a scalar. And lastly, we're going to look to find the magnitude of vector A. Remember, this magnitude notation can be used with the double vertical bars, or we can also just use single vertical bars to represent the magnitude of A. But either way, mag A is going to be determined by taking the square root of all the components squared and added together. So we'll say 4 squared, -1 squared, and 2 squared. This is going to give us the magnitude of that vector A, and so we'll say mag A is equal to the square root of 16 plus 1 plus 4, again that 21 inside there. So mag A is equal to the square root of 21. And of course that number looks familiar, so let's just take a moment to notice that when we found A dot itself, we got 21. When we found the magnitude of A, we got the square root of 21. And what we'll see in the next property is that the A dot A, or a vector, when we dot a vector with itself, what we're going to get is the magnitude of that vector quantity squared. And so we saw in this case that A dot A was equal to 21, and the magnitude of A was the square root of 21, and so that turned out to be the same thing as the magnitude of A squared. And this is actually one of the properties that we'll see in the next little bit.